The purpose of this video is to work through a few example problems that will test our understanding of the concept of multiplicity, or our spin-spin splitting patterns. So for this first example, what we are going to do is predict the multiplicity for each of the signals that is expected in the proton NMR spectrum for the compounds shown below. We will start with this compound that I'm circling with my laser pointer on the left, and we're going to go through and predict the multiplicity of each of the signals that we expect to see there. So first off, what we have to think about is which of these protons will we expect to see signals for? And thinking about that and the multiplicities of these signals, what I'm going to do is start just at one end of the molecule here. I'll start over here and start looking at each set of hydrogens individually to determine what the expected multiplicity of those would be. So at this position in the molecule, we would have a CH3 group in our line angle formula, and we only have one set or one position here that leads to vicinal hydrogens. That's the position right here. And remember, to determine multiplicity, we're typically looking at vicinal hydrogens. So to determine number of vicinal hydrogens, we look just over to here. And at this position, there would have to be just a CH2 group. The assumption we will make here is that those two hydrogens of the CH2 group are in the exact same chemical environment because of the fact that they are just part of a chain here of carbon-carbon single bonds. There should be free rotation around the carbon-carbon bond here, giving those two hydrogens equivalent chemical environments. They would be experiencing the same types of magnetic field, the same strengths of electron donating and electron withdrawing groups, making those show up indistinguishably in the eyes of the NMR. So for our CH3 group here, keeping in mind that the multiplicity, if we're looking at a simple splitting pattern, is n equals 1, where n is the number of vicinal hydrogens. And those vicinal hydrogens have to be on absolutely equivalent vicinal hydrogens. And so we're assuming that the two hydrogens in blue are equivalent to one another. They're indistinguishable. And so using our n plus 1 rule here, n would be equal to 2 because there's those two blue vicinal hydrogens, plus 1 equals 3, indicating to us that there would be a triplet at this position. And so I'm going to erase these sketches that I have made of my work that I was showing there and just write the word triplet in here. So I'm just going to write triplet. And another way that you'll commonly see this is just abbreviated as a T for triplet. So that's what we predict as the multiplicity there. We then come on over to our next protons in the chain, this CH2 group. And we already mentioned that we would expect that these two hydrogens would be chemically equivalent. They, due to the free rotation around the carbon-carbon bonds in this acyclic molecule, would be experiencing the exact same magnetic field strength. And so, as a result, they're going to behave as a single unit there. And when we look at those and we think about how many hydrogens are vicinal to there, and are those hydrogens that are vicinal all in exactly the same chemical environment as one another, or are they all in different environments? The only vicinal hydrogens that we see relative to the hydrogens in blue is we see the adjacent CH3 group there. If we go the other way over to this left, that's our carbon right here. There's no hydrogens directly bonded there, so there's no vicinal hydrogens going that way. And so at this CH2 group, what we would expect following the n plus 1 rule is that there are 3 vicinal hydrogens on this methyl group out at the end. All 3 of those are equivalent because the 3 methyl groups are all freely rotating. The 3 hydrogen atoms of the methyl group are all freely rotating around the carbon-carbon single bond out there. So they're all equivalent, meaning we can just plug those in as n equals 3 vicinal hydrogens plus 1 gives us a grand total of 4, and 4 represents a quartet. So what we'll be doing is filling in here with the term quartet, or Q for short. Then we come on over. At this position, there are no hydrogens bonded there, so we don't need to fill in anything there. We come out to the end of the line here, and we would see a methyl group here, also a methyl group here. And those two methyl groups, due to the expected free rotation around our carbon-carbon single bonds here, the bonds are not locked into a ring or anything, so we have expected free rotation. So these two methyl groups, we can anticipate, due to the symmetry of those, they're both bonded to the same carbon atom and we have free rotation to interchange them, we would anticipate that these two are going to show up as a single signal. So I'm going to circle those together because we're asked to predict the multiplicity of each individual signal, and these two sets of methyl protons are going to show up as a single signal due to the fact that they are in the exact same chemical environment. They are both directly bonded to the same carbon atom, and we can rotate freely around these carbon-carbon bonds to illustrate that those are going to be in the same chemical environment on average. So our two methyl groups there, if we were integrating this, they would add up to a grand total of 6 as our integral there, representing the 6 protons. And the multiplicity there, to evaluate that, what we do is we look at the vicinal position. And in our vicinal position, we come over, vicinal, remember, is on the adjacent carbon atom, so the adjacent carbon is right here. Looking at that adjacent carbon atom, there are no hydrogens directly bonded there. And so therefore, applying the n+1 rule, n would equal 0 because there's no vicinal hydrogens, plus 1 gives us 1, which means that we would have a singlet at this position. Singlet we can represent as S for our abbreviation there. I'm going to erase my scratch paper work there and just leave the term singlet in there as my final answer. Then what we do, coming on through, we said there was no hydrogens directly bonded here, so we don't need to worry about that. Carbonyl group has no hydrogens directly bonded. Coming over to the aromatic ring, no hydrogens directly bonded here. We already have a complete octet on that carbon, but we do have other hydrogens around the ring here that we need to contend with, namely here, 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 and last but not least, right here. So we need to think about these. And we also need to think about whether each of these 5 protons of the aromatic ring are going to show up as separate signals, or whether some of those are going to be interchangeable and show up as the same signal. And so what I've done is placed in red here these 2 protons. And as it turns out, these 2 will show up in the spectrum as a single signal right there. So we would have one multiplicity to predict that is going to apply to both of those. The reason why they show up as a single signal is we could think about rotating around this carbon-carbon bond here, this carbon-carbon single bond. If we rotate around that bond, flipping the ring over and over, these 2 protons become interchangeable. The one that's here could come over to here and vice versa as we rotate that ring around. And so those are indistinguishable due to the fact that we can rotate around that carbon-carbon single bond, and also essentially due to the fact that these groups here are symmetrical to the red hydrogens as well. If we had brought in something like a methyl group and put that on one position here asymmetrically in the aromatic ring, then that would change the chemical environment of the 2 hydrogens relative to one another. But here, since we have aromatic ring that has no substituents, it enables these 2 hydrogens to be in exactly the same chemical environment. And so to determine the multiplicity of that, what we do is we pick one of those 2 hydrogens, doesn't matter which one since they are equivalent, and we ask how many hydrogens are vicinal to that particular hydrogen. So this hydrogen here, we could choose as the hydrogen that we are looking at, and we ask how many hydrogens are vicinal to there. Well, there's just one as we come over to here. So one vicinal hydrogen is always going to give us, via our n+1 rule, n would be 1 because there's one vicinal hydrogen, 1 + 1 makes 2. So this is going to give us a doublet signal. So I'm just going to put the word doublet there. And doublet we can refer to as D. And again, we're keeping in mind that to assign this as a doublet, you just pick one of the two hydrogens here since they are totally equivalent, totally equal, since they are symmetrical in the molecule, interchangeable through rotation of a carbon-carbon single bond. And look at that one hydrogen of your choice and ask how many hydrogens are vicinal to that to come up with our assignment of doublet here. We come on to the next here, and these two blue hydrogens that I have shown would also be indistinguishable by NMR. They are going to show up, in other words, as a single signal because of the fact that they are perfectly symmetrical to one another within the aromatic ring, and we have that free bond rotation of the carbon-carbon single bond out here that could rotate and flip that aromatic ring around over and over again so that those two hydrogens would be exchanging positions, and they therefore are indistinguishable by NMR. So looking at those two protons in blue that would give a single signal, in this case, we have a couple of different vicinal hydrogens that go off in different directions. So from one of these blue protons, you can pick whichever one you want, look at how many hydrogens are vicinal. So we have a vicinal hydrogen here in light green. We also, coming the other way, have a vicinal hydrogen in red. So there's a grand total of 2 vicinal hydrogens here. And if each of those 2 vicinal hydrogens split the signal with exactly the same frequency, then we would expect this to follow the normal n+1 rule, where there's 2 vicinal hydrogens plus 1 would give us a triplet. But in cases where the 2 vicinal hydrogens are not completely equivalent, meaning they are not exactly symmetrical within the molecule as a whole, instead what we normally get is one of our complex splitting patterns because the chemical environment over here at the green proton is a bit different than the one over here at the red proton. The red proton, for example, is closer to the carbonyl group. And so that creates different magnetic environments for the red proton versus the green one. And those 2 hydrogens, the red and the green, that are both vicinal to the one in blue, are going to cause a complex splitting pattern because the green proton is going to have a certain frequency at which it will split the pattern. The red will have a separate frequency at which it splits the pattern, creating a more complex splitting pattern. And we could show that by thinking of, schematically, if we had our starting chemical shift. So we'll say this is the shift of the blue hydrogen. And then that chemical shift is going to get split by one of the 2 hydrogens, whichever one is the higher frequency coupling interaction, into that doublet. So we'd have 2 signals here and here. And then that takes care of the green proton that's coupled to the blue one. And then the other vicinal hydrogen over here has a separate coupling constant, so it's going to split that doublet that we created from coupling to the green into another doublet because we have coupled to the red proton there. So the doublet gets split into another doublet. And so as a result, that gives what we refer to as a doublet of doublets. Because of the fact that we have 2 vicinal hydrogens and those 2 vicinal hydrogens are not in the exact same chemical environment, they're in different environments, and so they each individually split the signal into a doublet looking to the green signal and another doublet looking to the red signal to create this doublet of doublets pattern. So it's going to be a grand total of 4 signals, which would show up in the spectrum as 4 signals of equivalent height. And they will be split by the frequency that the green signal splits the blue signal by, as well as the red signal splitting the blue one by. So doublet of doublets is what we would expect to see there. That's what you would need to have labeled. So I'm going to erase my scribble marks of showing my work here to get to that and just make this simple and labeled as our doublet of doublets here. So just to be clear, I'll extend my blue line down to here, indicating that's a doublet of doublets. And then we're down to the home stretch now. We have just this one green signal left. And our one green signal, that's proton in green, is connected to two vicinal hydrogens. We established that those two vicinal hydrogens that are both in blue are in chemical environments that are equivalent to one another. So the two blue protons are absolutely in the same exact chemical environment. And so they are going to behave identically in splitting that signal for the green proton. And so we can follow the n+1 rule here, where n+1 will be equal to 2 because there's two equivalent vicinal hydrogens, plus 1 equals 3. Therefore, that green hydrogen atom is going to show up as a triplet. So I'm going to go ahead and put in here my abbreviated term here, T, for triplet. So that will solve the multiplicities of each of the atoms in this. Let's do this same thing for another example problem here. So we now have our structure on the right, a small but mighty alkene that we will look at the multiplicities of. So in the case of this molecule, much like the other one, I'm just going to start at one end of the molecule and start working my way through. So at the right-hand end of the molecule as well, I will go ahead and start. And at the right-hand end of the molecule, we have 3 methyl groups here, here, and here. All of those methyl groups would be equivalent to one another because they're all bonded to this carbon-carbon single bond out here. And so that bond can rotate around freely, exchanging the positions of these 3 methyl groups. So in the container that these exist in, the NMR tube, what's going to happen is these are going to be quickly, freely rotating around that carbon-carbon single bond, making all 3 of these methyl groups equivalent. In other words, they're all going to show up as a single signal, that is quite a tongue twister for me, in the NMR spectrum. So this would end up being a total of 9 hydrogen atoms, would be the integral for this. The question, though, is asking for the multiplicity. So what would the multiplicity be here? The multiplicity, if we take our groups here, pick any individual one hydrogen out of these and look to the adjacent carbon for attached hydrogens, finding those vicinal hydrogens, we see there are no vicinal hydrogens here. We come to the adjacent carbon, no hydrogens there. So we can apply our n+1 rule, where n is equal to 0, no vicinal hydrogens, and n+1 equals a singlet, which I'm going to abbreviate as S here. Coming onward to our next hydrogen. Our next hydrogen will be the guy right here, which I'll go ahead and sketch in. And that particular hydrogen atom, when we think about what it is vicinal to, we can come over to here and find it's vicinal to this hydrogen in red. It is also vicinal to the hydrogen that I've just drawn in green. Looking to the right, there are no vicinal hydrogens at this position, so it's only these 2 vicinal hydrogens that are going to be coupled to the hydrogen in blue. As we think about the multiplicity of that hydrogen that is in blue, we have to ask whether the 2 hydrogens that are vicinal to it, the green hydrogen and the red hydrogen, are equivalent. Are they interchangeable? And the answer here is that they actually are not equivalent. The reason why they are not equivalent is we have this carbon-carbon double bond here. The carbon-carbon double bond does not freely rotate. That makes it very different than a carbon-carbon single bond. And due to the fact that we have a double bond here that can't freely rotate, the atoms are locked into place. The green hydrogen is permanently oriented in this cis configuration to the blue hydrogen, whereas the red hydrogen is permanently trans to the blue hydrogen. So these 2 hydrogen atoms are in different chemical environments. One of them is closer in space to this hydrogen in blue than the other, for example. And so as a result, these 2 hydrogens, the one in red and the one in green, are not equivalent to one another. They are distinct from one another because we can't freely rotate around a carbon-carbon double bond to exchange or interchange those 2 hydrogen atoms. And so those are each going to have their own distinct properties in terms of the frequency at which they will split the signal in blue. And so what we will have here is a doublet of doublets, which I'm going to abbreviate as DD, because what will happen is that the signal in green, the proton in green, will cause signal splitting of the one in blue into a doublet, and then the red hydrogen will cause splitting of that doublet into another doublet to give us a doublet of doublets. That would be analogous to what we saw with the aromatic ring over here, where we had a doublet of doublets as well. So that will be a doublet of doublets at the blue proton. Now we do the red proton. At this red proton, we can look at the number of vicinal hydrogens, which in blue, we see that there is one vicinal hydrogen. That is the only hydrogen that's vicinal to the one in red. However, there is also in green one so-called non-equivalent, non-interchangeable geminal hydrogen. Remember that geminal means hydrogens that are directly bonded to the same carbon atom, where vicinal meant that the two hydrogens are directly bonded to adjacent carbons. And so what happens here, this is a situation where we can actually have geminal splitting occur because this hydrogen green is not equivalent to the one in red. So in cases where we have two protons bonded to the same carbon and those two protons are in different chemical environments, they're permanently stuck in different chemical environments because they can't rotate around the bond, that is going to enable geminal splitting. And so here at this proton, we have splitting resulting from interaction with both the blue proton, that is vicinal, and the green proton, that is geminal. And that geminal splitting is something that you only need to look for in cases where two protons that are attached to the same carbon are non-equivalent. There is not free rotation around a carbon-carbon bond. They are locked into an orientation relative to one another. And so keeping that in mind, this signal actually at the red proton becomes another doublet of doublets because we have coupling to the green proton that is non-equivalent to the red one, and we also have coupling of that proton in red to the proton in blue. So it creates a doublet of doublets, a doublet originating from the green proton, another doublet originating from coupling to the blue proton. Similarly, if we come up to this green proton, we have the same sort of scenario where it is going to couple to the geminal proton here in red. It will also couple to the vicinal proton in blue, giving us a doublet of doublets here as well. So this illustrates to us the special scenario of where there is geminal coupling if the two protons are non-equivalent. So what we can observe here, just to summarize, is that geminal coupling, meaning geminal splitting of the signal, will occur if the two geminal hydrogens are non-equivalent, meaning they are in two different chemical environments permanently. And this business about them being in two different chemical environments usually occurs when there's restrictions on free rotation around bonds. So that is definitely the case here because when you have a double bond, you don't have free rotation around the bonds. Instead, the bonds are locked into place, keeping that configuration constant of where the red proton is located in the molecule relative to the green one. We don't have free rotation, and so that allows for geminal coupling because those two hydrogens are non-equivalent. They are not equal to one another. Instead, they show up as two separate signals in the NMR spectrum because of the fact that they're in different chemical environments, so they'd have slightly different chemical shifts, and they also are going to each engage in their own set of splitting patterns as well.